Hello and welcome to another episode. I'm pleased to be joined today by a fellow content creator, science communicator, and promoter of secular humanist rationalism, Dr. Blitz. Blitz has a PhD in mathematical physics. His expertise is going to help us answer the question of why should anybody care about quantum mechanics? The ways classical physics, chemistry, and biology influence our lives are obvious, but quantum mechanics is not. Because quantum mechanics is also misunderstood, it's used both intentionally and unintentionally to push a lot of bogus narratives, be it to undergird the latest Marvel movie or to convince someone that consciousness, God, and free will have been scientifically proven. Let's get started. Okay, Blitz, welcome.
Thank you. I'm glad to be here.
So I figured I would just let you introduce yourself in whatever way you want.
Yeah, sure. So I'm what you might call a young researcher. I finished my PhD last year. I work at a university in the middle of Europe. I'm not going to tell you where. And I primarily do research in a mathematics department. I work with some geometric structures of black holes and some more purely mathematical things involving conformal geometry. On TikTok, I spend a lot of time making science videos. And when I'm not doing that on TikTok, I spend a lot of time arguing with conspiracy theorists, right-wingers, and religious people.
Same. So your professional work, the scientific work that you do helps us understand more about black holes. That's what a lot of your research is focused in.
So it's actually something I've only recently got interested in. My PhD work was mostly, you could even say it was mostly mathematics. It definitely had applications to some work in physics, especially some of this like stringy stuff. But my PhD advisor was a mathematician who also got his PhD in physics, however many years ago. But in the last 6-9 months or so, I've made some new connections at various conferences, and I've started some projects on black hole stuff.
That's cool. That's really cool. So for you, how did you get into math and physics in the first place and then later decide that you wanted to do this as a professional?
I don't know how typical the story is, but so my mother will tell the story that I always wanted to be a scientist, right? You know, I was always drawing pictures of beakers or whatever, but I have this very distinct memory. I was hanging out with my best friend, Zach, at the time. We were just trolling around on the internet, early 2000s internet, right? And we stumbled upon like a picture of a black hole. I think it was from Brian Greene's Fabric of the Cosmos or something, some illustration associated with it. And I'm like, that's the coolest thing I've ever seen. I'm going to do that. And then later, I saw a PBS Nova special. Again, I think it was Brian Greene. He had it was either Fabric of the Cosmos or some other Nova special that he had. And I'm like, string theory is so cool. And Albert Einstein is so cool. And all of these things are so cool. And I was good at math. Like I was already pretty good at math. So I'm like, this is what I'm going to do. And so since I was 9, it was basically been like single-minded goal. I'm going to do a PhD and then I'll be a professor, hopefully. And you know, I'm just 21 years later, right? I even applied to go to Cambridge for undergrad. They did not let me in.
Oh, wow. I don't know. They probably accept somewhere like 5% of applicants or something like that.
Also being a foreigner, you know.
Yeah, that's true. So ever since you were 9 years old, that's awesome. That's a pretty cool character arc. I think that Nova is like one of the most underappreciated things.
Much.
It's so incredibly good. It's just so good. Okay, so we'll jump right into the quantum mechanics thing. So the first thing I want to do is eventually we're going to get to the point of like, why should like the typical layperson care about it? And also, but we're going to begin with just trying to understand it a little bit better. Because, you know, I have a degree in science, but it's biology. I care about this stuff, but it's tricky. You know, like the typical person, it's very hard to understand what quantum mechanics really is. So hopefully we can get some of that out of this. So my first thing is, what question or questions were scientists trying to answer that led them to discover quantum mechanics?
Oh, you're quizzing me on the history of quantum mechanics. Right. So there was really well understood physics, at least what they thought was really well understood physics, up until really 1899. It was thought that physics was done. They had a complete description of gravity, a la Newton in, what, 1666 or whatever. Maxwell formalized his famous equations in the late 1800s. I can never remember the year. And by 1899, they're like, well, that's everything. Electromagnetism is everything, and gravity is everything. Everything else is just, it's peanuts, right? And then I want to say it was 1900, I think, when Max Planck rolls around and says, hey, you know that thing that we couldn't explain, but what you thought was just not a problem? Well, it's actually a problem, and I have a solution. The story is something like that anyway. This was the ultraviolet catastrophe. There was a problem with predicting the amount of radiation that a hot thing gives off, right? You heat up a lump of metal, it glows, figuring out how much radiation it gives off, how much light it gives off, and what color that light is was a problem. And Max Planck came up with a solution, but the solution involved saying, look, the light waves that you thought it was giving off, they can only come in discrete chunks, right. Meaning it's not waves, it's particles. And from there, over the next, 25 years, quantum mechanics was entirely formalized, in no small part due to my boy Albert Einstein, who revolutionized 3 fields in 10 years.
Yeah, because Newton thought light was waves, and they had a good reason to think so, and then this overturned that. So I never heard that Planck sort of initiated that, but I did know that didn't Einstein sort of give us the concept of a quantum, or like a packet of energy? Because what he actually won his Nobel Prize in was the photoelectric effect, which has quantum mechanical implications, right?
Yeah, so the idea is that Max Planck said, what if light could only come in packets with this much energy? Mm. And that was like a what if. They had no idea at the time. And then 5 years later, Einstein is like, well, actually, we can prove that that's what happens. Okay. That's why he won his Nobel Prize.
Okay, yeah. He should have won
He should have won 3.
8, yeah, but well, I'd go way more than 3, but yeah. And then it's fun. We'll get to this later, but it's kind of funny. He then came to disagree with a lot of implications in quantum mechanics, and it's kind of funny. I guess maybe he was a little bit more of a classicist in that sense, but how can you be a revolutionary and then also be a classicist?
Because I think when he was doing special relativity and the photoelectric effect, he was in his 20s. When you get to be in your 40s and 50s, you become a little bit more conservative, generally.
That's a good point. That's very true. So what does Bohr fit into there as well too? Because Bohr's the one that originally sort of came up with the electron and the energy level and stuff like that. I mean, I may be mischaracterizing this, but he sort of indicated that the electron has this much energy when it's at this distance, and that energy is conserved.
Yeah. So, and yeah, you're really testing my knowledge. And I've told these stories enough time. I really should know it. But yeah, Niels Bohr was there was a whole group of maybe a dozen early 20th century physicists who were working on this. Niels Bohr was an instrumental character. He came up with this the Bohr model of the atom, which is basically what's taught in high schools. That was him. The reason why he came up with it was as an explanation to the following problem. It was well known. So the atom wasn't known about in Maxwell's time in the late 1800s, but the atom was discovered by Rutherford. I want to say Rutherford and his colleagues. I want to say in the 1912, maybe. I could be getting the year wrong.
Yeah, we knew the electron existed, but we didn't know the proton existed until I think it was 1911 or 1912.
Yeah,
and then,
something. Right.
And then the neutron later.
But if you have a proton and neutron, and then you have the electron orbiting it, they had established that. The trouble is, classically, whenever a charged particle accelerates, it gives off electromagnetic radiation. And what we know from classical mechanics is that when you go in a circle, your velocity is changing. It's changing direction as it goes around. And so the electron should have been giving off radiation if it was just orbiting classically, like how a planet orbits the sun. And there were some calculations. I don't remember who did this, but there were some calculations that were done. It basically said, look, hydrogen, the simplest atom, should be unstable. The electron should fall into the center in like a fraction of a second because it just gives off energy and then it spirals in.
Yeah, it loses energy and gets,
Right. So Bohr came up with the solution. He said, look, it can't give off energy if it can't change its orbits.
Huh. That's really simple. I never heard it framed that way, that I'd heard that what is keeping it from spiraling into the nucleus? Well, it just simply must occupy there's like 7 or 8 energy levels or whatever. But I guess I never heard that it gives off radiation as it moves because its velocity changes. That's interesting.
Yeah.
I never heard that before. Okay,
And
so go ahead.
Oh, I was just going to say, funny story. You might say, well, isn't that a problem for Earth? Earth is going around the sun. Won't the Earth spiral in? And it would in like 2 trillion years. Gravity's really weak.
2 trillion. Well, yeah, the sun won't exist.
Yeah.
Far long before we get to that point.
Yeah.
Okay, so I think people that kind of know what quantum mechanics is, people that are just like barely initiated with it, like I kind of have to know about it because I sort of have to teach it in some aspects, but I'm definitely not an expert. So we would summarize it. We would say it's, or at least part of it, is the idea that something can be in more than one place at once unless or until you look at it. So that's like part of quantum mechanics, right? So that's probably terrible. So can you explain quantum mechanics in an intuitive way?
Yeah. So first I have to say, the way that you learn quantum mechanics when you're, say, a grad student or whatever, you learn it in a very standard way. And it's basically the same way it's been taught for probably almost 100 years now, maybe 80 years. So there's a particular interpretation. I imagine we're probably going to be talking about that at some point later on down the line that they teach because it's easy to teach and it's fine. But most of what I'm going to say about quantum mechanics, at least as far as philosophical implications and so on, comes directly from Sean Carroll. So I don't know if I can do a book plug here, but Sean Carroll wrote a great book called Something Deeply Hidden. Man is brilliant. I learned general relativity from his textbook. He's now a philosopher of physics. Anyway, writes a great book that talks a lot about quantum mechanics. That's all to say. I cringed a little bit when you said what you said.
Oh,
because not because it was wrong per se, but because it implied a specific interpretation.
Oh, okay. Cool.
So the idea is as follows. Experimentally, what happens is that, let's say you have an electron. It's just doing its thing, sitting in a box. And the way that you might try to figure out where it is you just bathe the box with light. And electrons, being charged particles, they can interact with light. They can absorb photons, release photons, and so on. Photons can bounce off of them. You bathe it in light, and then you wait till one of those photons, one of those light particles, kind of bounces off at the wrong angle, and then you go, aha, the electron's there. Now, what you find if you do this experiment over and over again is that even if you just put the electron in one place and let it go and just don't even touch it, it'll be in different places all the time. Or alternatively, we could think of it perhaps, it's a little bit trickier if we don't think of position, but there's this notion called quantum spin. You can just think of it as the electron spins clockwise, the electron spins counterclockwise. And if you just plop down an electron in your lab and you measure its spin, whether it's counterclockwise or clockwise, depending on how you set it up, it seems to be random. You'll get clockwise half the time, counterclockwise half the time, maybe it'll be 70-30. Maybe you'll get counterclockwise every time because you set it up in a particular way. But the point is that there seemed to be something fundamentally probabilistic about quantum mechanics, which was completely foreign, considering the world of classical mechanics is, you give an input, turn or crank, you get an output, it's exact to your degree of accuracy. That was very strange. And so the best explanation that could be come up with was that, and we have Schrodinger to thank for this, is that we shouldn't think of electrons as just a tiny billiard ball, or photons as a tiny billiard ball just floating in space. We should think of them as a wave that obeys a wave equation, which has a name now, the Schrodinger equation. And that wave will tell you roughly where the electron is likely to be, but it won't tell you where it is. The wave was completely deterministic. You can always predict the shape of the wave at any time. But when you go to measure it, something happens, and somehow, we can talk about the causes later, it picks where the wave is strongest. It picks randomly from where the wave is strongest. It might be that it has 3 peaks, and so it'll pick evenly between one of the 3 peaks for where the electron is. So it's just this very, very strange notion, very, very deep departure from classical physics, where things don't behave deterministically anymore, at least seemingly. And so quantum mechanics is the answer to that. It's how we understand reality. And as far as anybody can tell, it is what reality actually does.
Cool. So when I teach, and keep in mind, I have to try to explain this to like 15-year-olds. So
Totally reasonable.
when I try to explain this, I typically like show them an orbital, and I'll say something to the effect of, we can't know where in the orbital the electron is. It could be anywhere. In the past, I've perhaps said you can think of it like it is everywhere in there. It's in a superposition or whatever, until we look, and then it manifests itself in one place. But once we do that, then we can't know where it's going to go next, because you can't know two things at the same time is like the basic problem.
Yeah, so you're touching on the Heisenberg uncertainty principle, which seems very spooky. And so for those who are listening and don't know what it is, the Heisenberg uncertainty principle says, if you measure the position of something, you can't know its speed. If you measure its speed, you can't know its position. There is a fundamental uncertainty there. You could measure its position with some fuzziness, and then you can measure the momentum with some fuzziness, but you can never get exact precision for both. And it is true. And it seems spooky. It's like, well, maybe we just need better devices, right? But it only seems that way in the intuition that we've developed, evolving on the plains of the Serengeti or wherever we did, right? We picture things as solid objects that have places and speeds. But if you throw away that notion, if you think of them as, look, an electron's just a wave, well, this makes total sense for waves. A wave is, if a wave is just one wavelength, it'll be spread out. Or you can add up a whole bunch of wavelengths together, and then you can have it be localized. But when you do that, now your wavelength, which is kind of related to your speed, your momentum, now your momentum's not well determined, but your position is. So it's just a straight duality. And for anybody who's mathematically inclined, this is a Fourier transform. That's all that it is.
Okay, cool. I'm going to skip that one and do that question later. But so my next thing is, it's not just, average people like me who struggle with quantum mechanics. Einstein, or talked about this earlier, he famously hated some of the implications of it. So you kind of already touched on this. Why do you think that is? And I assume he wasn't alone. Were there other, but I don't know, like any big names that were like, no, entanglement, that I won't believe it, or the way it's just indeterminable. I can't believe that. Were there other people that were in that camp?
Yeah, there were a few, and they came later. Einstein wasn't stupid, and he wasn't being conservative. Well, I mean, he was being conservative in his own way. The trouble is the prevailing understanding of quantum mechanics at the time was the so-called Copenhagen interpretation. It's the one that's still taught in school, by the way, which is basically this idea that you have your wave function. This is the wave that describes your particle. And when something observes it, whatever that might mean, the wave function collapses and it just picks a place, and everything else goes away. And furthermore, so that's something to keep in the back of your head. Already problematic for Einstein. But furthermore, this property of collapse applies to entangled particles. Now, entangled particles are just are just particles that are really shouldn't be thought of as separate things to begin with. They're fundamentally inseparable. You can separate them spatially, but the way that we describe them mathematically is with one linked thing. And so the idea is that if you observe one of them, it'll collapse the wave function of both of them. And Einstein had a problem with that, because Einstein, being famous for his special and general relativity, he understood this to mean, perhaps in a justified way, that this meant that something was breaking the light speed barrier.
Yeah.
He called this spooky action at a distance, that something could happen instantly. And he had a problem with that. And for what it's worth, I also have a problem with that.
Yeah, well, Copenhagen's not the interpretation you prefer, right?
No.
We'll get to that really, really soon here. Was there anything else you wanted to add about that?
Yeah, so Einstein was in the minority in the first. Einstein died in 55, I think. Yep. He was in the minority in the first half of the 20th century. And I mean, in some sense, he still is. The Copenhagen interpretation, if not the majority, is the plurality of physicists. But by the time the late 50s, early 60s, and 70s rolled around, there was this growing movement of people who were like, yeah, maybe we don't need this Copenhagen business. So yeah, it's just to say that, as always, he was before his time.
Yeah, with basically everything, even the stuff he was wrong about, like the cosmological constant when we figured
Yep.
out that there's dark energy. I was like, well, you were right, even when he was wrong. We talked about Sean Carroll, or you mentioned him a bit ago. So he did a 4-hour solo podcast a couple days ago.
I haven't seen it yet.
Called The Crisis in Physics. I listened to about an hour of it, I think. And in it, he says that no, quantum mechanics and special relativity actually do work together. And I've never heard that before. So maybe starting with a simple explanation of what special relativity is. Can you give a fairly simple explanation of how they actually do work together?
I'll do my best and make no promises. Right.
Yeah,
So special relativity, you may have heard that you can't go faster than the speed of light. You have special relativity to thank for that. The idea is Einstein started with this very simple postulate, and there's history behind this, but for the most part, this is fine, that regardless of how fast you're going, the speed of light always, or like a light beam always looks like it's going the speed of light. Whether if you're on a train and you turn on a flashlight, from your perspective, the light goes at the speed of light, but from someone on the ground's perspective too, the light also looks like it's going the speed of light. Very counterintuitive. I have had plenty of arguments with people. Flat earthers actually hate this usually. I've had plenty of arguments with people who think that this is nonsense. Unfortunately, it is arguably one of our best tested scientific theories that we have access to. And so Einstein was right in thinking that there is something sketchy here. If something appears to violate special relativity, you have a problem. General relativity is a little bit more wishy-washy, but special relativity is pretty good. So what Sean Carroll was referring to is quantum field theory. So we have quantum mechanics. This is like electrons just kind of like moving slowly, doing their wiggle wobble things. Nothing fancy is happening. You don't have antimatter. You just have like a particle, like an electron hanging out near a nucleus, right? But we know that things behave differently when things start to move near the speed of light. And for example, in a gold atom, the reason why a gold atom is gold is because the electrons that are close to the inside of its maybe I'm wrong about this. This is folklore I've heard. So if somebody fact check me on this. A gold atom is gold because of relativistic effects. Namely, the electrons are like their orbit is changed in such a way because they're moving so quickly.
I've heard that's why mercury is a liquid, because there are relativistic effects. Yeah.
In heavy atoms, that tends to be the case because they have a lot more protons, and so their pull on the electrons, on their inner electrons, is very, very tight. And so tight orbits means very, very fast motion from a classical perspective. Right. So clearly, we can't just treat electrons using classical mechanics or non-relativistic mechanics, because different things happen. And in fact, Dirac, however you pronounce his name, he was trying to come up with a way to describe relativistic particles, because one thing that was known is that you can take an electron and you can accelerate it to near the speed of light. This is known in the early 1900s, maybe by the 1930s, I guess. You can accelerate it to near the speed of light, and then it doesn't work so well. So Dirac comes up with this equation called now called the Dirac equation, which is sort of the first merging of special relativity and quantum mechanics. And one of the things that he observed, or not observed, he stumbled upon, was something that he called the Dirac sea. We now know that better as antimatter. His equation that was just trying to describe an electron at relativistic speeds predicted antimatter. This notion of negative energy particles. They're not actually negative energy. It's just they behave as if they're moving backwards in time, which corresponds to negative energy. Don't worry about any of that. It's technical details. Okay, so there's this business of antimatter. Great. So positrons, that's what they called them, the anti-electron. And then particle physics started happening in the 50s. And there was some quantum field theory that was developing, but it was not super well developed. Quantum field theory, by the way, being the way that that they described particles that are moving in a relativistic way. And so the idea is that instead of talking about an electron as a single thing, and then another electron as a separate single thing, instead you can kind of think of this as you have like an electron field, not an electric field, an electron field. And the reason why you would want to think of it that way is because you can think of an electron as being a bump in one direction on that field. Think of like a sheet of paper with a bump on it, and a positron being a negative bump. And now they can combine and cancel out.
Yeah.
And or if you dump enough energy into it, you can make new bumps pop up. So now you have a way of talking about collections of particles, and you don't have to worry about a single particle or a two particle or whatever. The problem with the Schrodinger equation is that it can't handle changing the number of particles. And it turned out you needed this energy mass equivalence in order to be able to talk about this at all. So you have special relativity on one hand, talking about how you can convert energy into mass, and you have quantum mechanics on the other hand, describing these fundamentally wavy particles in big air quotes. And you end up with quantum field theory, which is kind of the workhorse of your average particle physicist anyway, and has been since the 50s, really. And this is not up for debate. One of the quantum field theories that is arguably the most well known is the one that you'll first learn in a grad level course on quantum field theory is quantum electrodynamics. Richard Feynman and one other guy whose name I can't remember is responsible for it. This is what he won his Nobel Prize for. And it is, yeah. Well, the diagrams and the rest of the whole theory. This is the most accurate theory humans have ever come up with. It is accurate to one part. The predictions made by quantum electrodynamics agree with experiment to about 1 part in a trillion. 12 decimal places, they agree. It's remarkable. And so there really is no problem with special relativity or quantum mechanics. They play great together. And in fact, it just shows how strong special relativity is. It doesn't just describe a rocket ship going near the speed of light, or what happens to a twin when they go far away and then come back. It also describes how particle colliders work. And the fact that we're able to make such spectacular predictions says that we're definitely doing something right.
Yeah, I actually have this later on, that quantum mechanics is the most successful and accurate scientific theory of all time. But you're saying it's specifically this thing that Feynman came up with.
Yeah, it's the easiest.
Electrodynamics. That's what.
Yeah, it's the theory of how electric charge interacts with the electromagnetic field, light.
Oh, awesome! That's so cool. Okay.
Yeah, it's the simplest of the quantum field theories, so it makes sense that we would be able to test it most accurately.
Yeah, simple.
It is. I have some videos on it where I actually do the calculations.
That's cool. So there are now we're really going to get into it. So there are different interpretations for the collapse of the wave function. The way I understand it is basically the difference between how some physicists think about quantum mechanics versus others is just down to the collapse of the wave function. Is that pretty much?
If only it was that simple.
If only it were that simple. Well, maybe we can pretend it's that simple for right now, and you can get into more of it.
Yeah.
I'll finish the rest of it. So, what I want to know is, I hear that and I just go, okay, so what implications do these different interpretations have for the real world? And is there anything we can see every day that we would never see the same way if we solved this problem?
Okay, so it depends on whether or not the person who's thinking about the real world actually cares about what the universe is. So if you're just a guy, just doing your thing, going to work, taking care of your kids, playing some, I don't know what kids, Fortnite, right?
Yeah.
There's going to be no technological developments depending on regardless of which interpretation ends up being correct. That's not going to happen. It's been said in the past, and I'm being slowly convinced that this is not actually the case, but it's been said in the past that the reason they're called interpretations and not theories is because they make identical predictions. Now, this is arguable. Sean Carroll's made a case that these actually are testable theories, that you can differentiate them experimentally. It's just never been done because you need very, very rapid and very, very sensitive experiments to do so. So, but I mean, so the idea is that there's, yeah. So the way to think about this is that there's there's a wave function. Every interpretation of quantum mechanics agrees that there's a wave function because the Schrodinger equation is remarkably accurate, makes great predictions. So there has to be a wave function. And then there's this thing called the Born rule. This was come up with by a guy named Max Born, I want to say, again, one of those early 20th century quantum physicists, right? He won a Nobel Prize for this, actually. There were so many Nobel Prizes for like low-hanging fruit back then. Yeah, so the Born rule basically tells you how to convert the wave function, which is just a formula. It's like, x squared or something like that. It'll be some formula that tells you, it'll spit out a number when you input a position or something like that. It tells you how to convert that formula into a probability of measuring something, right? And like that's super important, right? Because if this wave function is completely inaccessible, if you have no way to connect the wave function to reality, well, then it's not a physical theory at all. So the Born rule is super, super important. And the real question is, where does that thing come from? Why is it that the Born rule works? Why does it and the details aren't super important, but it's a very simple, like you just square the wave function and that gives you the formula to calculate probabilities. Why is it that works at all? Now, the Copenhagen interpretation says something along the lines of, look, the early Copenhagen interpretation was, look, when you measure it, whatever that means, the wave function spontaneously collapses and it chooses to collapse at a location determined probabilistically by the Born rule. So if your wave function was 75% in one place and 25% at the other place, 3 of the 4 times it will collapse and end up at the 75% place, and 1 of the 4 times it'll collapse and end up at the other place. And this is just a spontaneous collapse that happens upon measurement. That's the Copenhagen interpretation. It's a little bit more sophisticated now. We can talk about things like decoherence, but it doesn't really matter. The idea is still the same. Then there's the many worlds interpretation, second most popular interpretation. This is the one that I think is most correct. It's probably most accurately called the Everett interpretation. If only because Everett was the guy who came up with it, and many worlds implies like Marvel stuff. But the idea is that when you go to make a measurement, the wave function doesn't do anything. You just entangle yourself with it. And so let's take the example where there's 1/4 of the wave function is in one state, 3/4 is in the other state. 1/4 of you will entangle with the 1/4 state. 3/4 of you will entangle with the 3/4 state, and you just won't be able to talk to each other again. So it's almost as if the universe splits. It doesn't. Like, it's still occupying the same space, it's still the same, it's still just one universe. But in some sense, the 3/4 you thinks that they've measured 3/4. The 1/4 you thinks that they've measured 1/4.
Do you think this is where people... I'm going to ask about this later, but is this sounds like the source of people saying, like, consciousness causes the wave function to collapse or something like that.
So the thing is the Copenhagen interpretation is what gets people on that, because it's the Copenhagen interpretation where some sort of measurement causes collapse. In the many worlds interpretation, there's no collapse at all. Collapse just doesn't occur. Oh, okay. You just entangle with it in different ways.
Yeah, I was thinking like becoming one with it is sort of the connection there, but now I see what you mean.
So what's happening is that so entanglement is just, like, we talked about it briefly, but entanglement is just this phenomenon that basically says your wave function mixes with its. And that makes kind of sense, right? Like you can imagine doing a measurement as like reaching out and like touching it. And so like you're going to interact with it, it will affect you, you'll affect it, and so they're gonna get mixed up together. And so when you reach out and measure it, you're going to measure it in both places, and you're made of electrons and protons and neutrons. So you have a wave function, and so your wave function will interact with both pieces, and it'll split. This is a process called decoherence, and so that's roughly the Everett or the many worlds interpretation in a nutshell. There are a few others. There's an interpretation called there are interpretations called dynamic collapse interpretations, which say, look, the wave function collapse doesn't have any, like, wave function collapse is real, but it doesn't have anything to do with observation. It just happens to an electron once every 300 million years. And if you have a lot of electrons, then it'll happen pretty frequently for large objects. And once one electron collapses, they all do. So that gets you a way of basically having very, very rapid collapse when a macroscopic object observes something. And then there's other ones. The one other one that I think is relevant is pilot wave theory, or also known as Bohmian mechanics or de Broglie-Bohm mechanics or whatever. This is actually a completely deterministic theory of quantum mechanics, which basically says you have the wave function doing its thing, evolves under the Schrodinger equation, but then you have an actual particle that kind of just rides the wave function like a barrel. And we don't have access to where the particle is. The wave function just tells us where the particle is likely to be. But it evolves completely deterministically. There's nothing random. We only measure the particle, but we just didn't know where, we just can't figure out where it is because we don't have access to that information. But it's completely deterministic. It's called a hidden variables theory. So those are like kind of the four big ones, I would say. There's another one called quantum Bayesianism, but I don't understand that well enough to talk about it on a podcast. So
sure. So would you say that if we take like the two main, which are the Copenhagen and the Everett, do people fall into favor with one versus the other just simply based on like philosophical or metaphysical preferences to them, or is one experimentally more verified than the other, or is it a mixture of both, or what do you think?
So the Everett and Copenhagen interpretations, as far as I know, have never been experimentally distinguished. In a sense, it's like an aesthetic thing, right? So on the one hand, with the Copenhagen interpretation, you have one universe. When you make a measurement, there's only one outcome, kind of matches with what we would expect. But in order to get that, you have this extra baggage of this thing that was just made up, this idea of wave function collapse. There's no formula for wave function collapse. It's just a thing that somebody said happened, and it gives you the right answer. The Everett interpretation is basically what happens if you take quantum mechanics and throw away everything that we don't have evidence for. All you're left with is just a wave function. You know, everything has a wave function. Electrons, we're all made of electrons, protons, and neutrons. Everything's quantum, and then you have the Schrodinger equation. That's it. Now, the consequence of this is that when you make a measurement, you split. That's just a direct consequence of pure quantum mechanics in its most raw form. So in some sense, I mean, at least for me, aesthetically, maybe not aesthetically, metaphysically, I take the position that, look, we shouldn't be making assumptions just because it feels better to our brains. I mean, it does give some weird sense, like it does play with the notion of identity a lot, because what does it mean if you split? Like, are they both you, or which one is you? It becomes like there's some real philosophical problems there. But that's what, like, I mean, that's where to me anyway, that's what the science says. We just have to reconcile with what it means.
Speaking of the interpretations between like Copenhagen and Everett, it kind of seems like you're saying, I'll draw a comparison to evolution. We had the theory of evolution before we knew how organisms actually acquire those inherited differences. And so once we learned that, once we had genetics didn't like disprove evolution in any way. It confirmed it. But what it did do was it opened up a brand new paradigm of sciences. And so it sort of sounds like you're saying, if we ever do solve this problem of the wave function, you know, it won't create a new technology or anything like that. So are you kind of saying that you don't think it would open up a brand new paradigm of science or physics?
I mean, it's hard to predict, right? But I honestly don't think so, because there's nothing that we can do to manipulate these things. Like say many worlds ends up being true. That's what I'm rooting for. You can't manipulate the many worlds. You can't talk to each other. So what's there to do? And let's say, and now actually, if the Copenhagen interpretation works out to be true, that could have some serious implications. Especially like the observer effect is generally well regarded as just not a thing. But if it turns out that actually the whole solipsism thing, like some sort of consciousness is required, like there's some like ethereal, clearly I'm a materialist, right? Some sort of ethereal consciousness required to collapse a wave function. Now you can have like telepathy. You can have like telekinesis and stuff where you just have like people's consciousness do it. So that would have that. I mean, It probably wouldn't. It probably would just be some like quasi-statistical thing happening. But like depending on how the Copenhagen interpretation worked out, it could have huge ramifications. But I also think that the Copenhagen interpretation is wrong. So I'm not betting my horse on that one.
So it sounds like if Copenhagen is true, then the X-Men could theoretically exist. Whereas if Everett is true, then that will allow me to believe that the Broncos win the Super Bowl every single year, just not necessarily in this universe.
It's not even that. Honestly, it would be better if the Copenhagen interpretation were real, because then you could have like quantum manifestation, you could like, all of that lovely stuff, right? But like if the many worlds like the thing is the branching only happens for quantum mechanical measurements. So like classical things just don't branch the wave function.
Darn.
So but even worse than that, the many worlds interpretation has some serious ramifications for what personal identity is. Like it could drive some people into like what are they called, existential crises.
Yeah.
So I mean it might in my opinion it's probably the true one, but it's not the fun one.
So the next question then is, how does quantum mechanics affect my day-to-day life? What do I depend on it for, or an understanding of it for?
Yeah, so I mean the obvious answer here is everything that's electronic.
Yeah,
right?
Like the transistor.
Yeah, the transistor. And funnily enough, the guy who invented the transistor is the only guy to have won 2 Nobel Prizes in the same field. He won 2 Nobel Prizes in physics, one for the transistor and one for, I want to say, superconductors. Big deal guy. He's not known about nearly as well as he should have been. Anyway, but I should have fact-checked that before I said that. It doesn't matter. People will get mad at me in the comments if I said something wrong. Yeah, the transistor is a big deal. I don't actually know if the understanding of quantum mechanics was necessary, because like people were playing with electronics. I imagine it probably was, if only because the way to come up with how these things work probably sped up the process of developing the electronics much more quickly. I mean, it's one of those things where like you could probably have just figured out by trial and error without actually knowing the underlying business. But that would be my first guess as to the thing that impacts you the most. But perhaps less well known, like radiation therapy. All of radiation is quantum mechanics. If you know what a PET scan is, it's often used for detecting cancers and like thyroid cancer and so on. Mm-hmm. That's positron emission tomography. That's antimatter.
Really?
Like, it's antimatter. They shoot you with antimatter
because it's positron. I never thought of. I knew it stood for positron, but I never thought about that.
So not only is it quantum mechanics, it's quantum field theory, and which involves special relativity and quantum mechanics.
Huh.
I
never thought about. I never realized that it was right there.
Superconductors too. So CT scans, they have superconducting magnets in them.
Would an MRI because it rearranges the, I don't really know.
I'm sorry, no, MRIs are the magnetic ones, right?
Yeah.
There's some medical scanner that's really, really loud and it spins really, really fast.
Yeah, that's the MRI. Yeah.
Okay, then yeah, that's the one that has the superconducting magnets in it.
Oh, right.
So anything with superconductors, anything with radiation, anything with transistors, like really our entire modern world. Like Marie Curie knew about radiation. Well, I don't know. I guess around the time quantum mechanics was being developed, but you don't have to know how it works to use it, but it certainly makes inventions more efficient. Like modern, smoke alarms use radiation.
Yeah, americium. Yeah. So that I did know.
Like basically everything.
Let's go. Yeah. So what you said you don't have to understand it to to see it, but if you want to invent technologies that take advantage of it, I would say, yeah, you do have to understand it. And I have no idea how many lives the MRI has saved, but it can't be less than hundreds of thousands. It just can't be.
The other thing that's quite interesting is we're actually, you may have heard of Moore's law. I imagine you have.
Yep.
With transistors.
Yeah.
So it's this thing where transistor density just increases exponentially, and the transistors get smaller and smaller, which is great. Except when they get too small, you run into quantum mechanical issues.
Yeah, now
which is
the
a problem
atoms.
Yeah,
Yeah.
yeah, it's a problem that you have to overcome now. And you know, if you didn't know anything about quantum mechanics, you'd be like, why aren't my transistors working when I make them smaller? So
That's a good point. That's not a problem a lot of people have, but
no, but it is a problem for like Intel and HP and Dell and all of these computer or I guess Intel makes chips. I guess HP and Dell don't.
yeah. Huh, cool. So, yeah, I knew about some of those, but I thought it would be interesting to let, because this is sort of for average people. Again, the title is Quantum Mechanics, Who Cares? Or So, I haven't decided what the title is yet. It's either going to be So What or Who Cares? But yeah,
Sure.
it does affect our day-to-day lives for sure.
I have more.
Go ahead.
So, it's the reason why the sky's blue.
Oh, Rayleigh scattering is
Yep.
quantum mechanics.
Well, it's classical, but it requires treating light as photons.
Oh yeah, because it splits the white light.
Yeah. So I mean, like, a lot of these things, a lot of like the scattering stuff is quantum mechanics. Yeah. So there's a lot that is. I mean, like, it doesn't matter why the sky is blue, but hey, it's interesting to know anyway.
There are some butterflies that have blue. I think it's blue morphos. I'm not sure, but they have blue wings. But if you get them wet, they're green, and it's because they have scales that interlock almost like a tree lattice. It's very weird, and the light goes in. And I don't remember the specifics of how it works, but the only light that can get out is blue. So they're not blue because of the conventional sense of absorbing all wavelengths and then reflecting. Technically, pretty much everything reflects all wavelengths. It's just whatever's dominant is the color you see. But that it actually, I don't know, the light breaks apart or only the blue bounces directly back to. I can't remember the exact mechanics.
Yeah. It's a non-pigmented color. There are other things too that are like perhaps more technical, but like it is now being more and more understood that, like, for example, chlorophyll uses quantum mechanics, quantum tunneling, in order to like be as efficient as it is. And there's like some protein folding stuff or something. I don't know a whole lot about biology, but I know that there's like some like biological phenomena that happen that actually require quantum mechanics to explain.
Huh. That. Didn't know that. That's awesome. So is the universe fundamentally quantum? Is it fundamentally classical? Or does it depend on what question you're trying to answer? Or can it be both? It seems like it can't be both. It has to be one or the other. But maybe, I don't know.
So fundamentally, I mean, who knows, right? But it seems like fundamentally it's quantum mechanical. There's this thing called the Bell's theorem. John Bell in the 1960s, I want to say 1965 maybe, wrote a paper about basically, and actually he was very fond of the pilot wave theory. In fact, he wrote it because he wanted to try to prove this. He wrote a paper where he described basically a way of testing whether the universe is fundamentally quantum or not. This is the famous Bell inequality. And if anybody paid attention to the science news in the last year and a half or so, there was a big Nobel Prize awarded in 2022 to 3 physicists, all of whom did work testing the Bell inequality. And it seems pretty conclusive. Basically, there's been a lot of testing done since the 60s, really, to try to kind of close loopholes in these experiments that test this thing. But the general idea is that, yes, our universe is fundamentally quantum, meaning that it's fundamentally governed by something like the Schrodinger equation, if not the Schrodinger equation itself. Now, that doesn't mean that you can't use classical mechanics. Newtonian mechanics got us to the moon. General relativity makes astoundingly accurate predictions for the motions of stars. But the point is that these are all kind of zoomed out approximations of what's truly happening at a fundamental level.
Cool. Yeah, I mean, it seems like, well, how do I want to say this? The world we experience, like, is this macroscopic thing that doesn't behave quantumly. You know, it behaves classically. But, you know, if matter fundamentally is composed of, you know, the things that make up the standard model, well, they're all quantum. I mean, they obey a quantum system. So I would, yeah, that I was gonna guess that you were gonna say it's probably fundamentally quantum, and the classical nature of matter is just an emergent property, I guess. It sort of comes out of it. I can't remember what you call that.
Decoherence?
No, I actually just learned about this today. It's let me open it up. I have it right here. Philosophers call these like category errors, but physicists call it decoupling scales.
Yeah.
Or
Okay.
like the details at small scales don't matter on large scales, basically.
Yeah.
So it seems like maybe classical mechanics is that, I guess.
The idea is that, like, look, your electron has a 99.999% probability of winding up in the vicinity of an atom, right?
Yeah.
And your electron's very, very small. So 99.9 whatever percent of the time, your electron's just going to be in the atom, and you're made of a trillion atoms or something like that. So maybe that might be too many trillions. So like, it doesn't matter where the electron is around your atom. It just matters that it's there, right? And it'll still do everything that you need it to, and it'll behave effectively classically from your perspective. Now, there's this notion of decoherence. When you have a large number of quantum systems all interacting, which is what microscopic things are, they split. They do the wave function splitting thing. And so when that happens, you end up with a decohered state, which are basically just a bunch of different copies of effectively classical systems. They don't interfere with each other anymore, and so you just end up with kind of like classically behaving things.
Okay. Because we were talking about Nobel Prizes, I looked into that physics one. Yeah, John Bardeen, it was superconductors and the transistor.
Yeah.
I don't remember what his name is, but I'm pretty sure it was last year. The guy that won the Nobel Prize in chemistry, he had won a Nobel Prize in chemistry before. So now
okay. I guess my knowledge is outdated.
Yeah, I think there are only 6 people. It's either 5 or 6 people that have won 2 Nobel Prizes, and Bardeen's still the only person to win it in 2 of them in physics. But then the other guy, yeah, there are 6 now because this website's outdated. He's won 2 in chemistry now. So
okay,
good for him. So my next one about the quantum mechanics, so what section is what is quantum tunneling?
Okay, so I have this thing in my hand. For those who are just listening, it's like one of these grip strengthening things. I've been playing with it as a fidget toy. There's a wall right here. You can't see it, but there is a wall. Now, I'm not a strong guy. If I threw this at the wall, it would probably bounce off. And the reason why is because there's electrons in this thing and electrons in the wall, and they repel each other. So it would take a certain amount of energy to make them push past each other because there's a repulsive force. But wave functions describe electrons, not billiard balls. So we really shouldn't be thinking of these as just billiard balls pushing off against each other. We should think of them as wave functions overlapping. And the idea is that when you have a repulsive force between two things, the wave functions overlap less. The wave functions are kind of pushed out. But wave functions go on forever, always, in all directions, with very few exceptions. So the idea is, and remember, the wave function tells you how likely it is to find something somewhere. So the idea is well, this thing, it has a wave function that's like part of its wave function is already on the other side of the wall. And so it has a very small chance of just being measured to be over there without ever having to pass through the wall to begin with, which is basically teleportation.
Yeah.
But you can think of it, I mean, the word tunneling is indicative here. You can think of a ball trying to roll over a hill. The ball would need a certain amount of energy to get up over the hill, even if the other side was lower energy. Or maybe you just attach a little drill bit to it and it just tunneled through the hill. Now it doesn't need as much energy. It can just go through for free. It's just very rare that happens. That's all quantum tunneling is. It's just this phenomenon where things kind of slide past energy barriers because their wave function kind of leaks through.
Yeah. And we know that this happens. This isn't like a theoretical thing because it causes, I don't know if it's transistors or what, but it causes actual problems in computing.
And it's actually, not only does it cause problems, it's actually utilized in technology. Scanning tunneling electron microscopes use tunneling to get images of individual atoms.
Oh, okay.
Basically, they have a tungsten tip, which is 1 atom thick. and it has electrons on the end. And they put a voltage on it, and the thing that they're trying to measure, if it gets sufficiently close enough, it's not going to touch the thing, but if it gets sufficiently close enough, like a few atoms away, an electron from the thing it's trying to measure might tunnel its way and jump to the tungsten. And you can detect a current.
How do people do that? How do people
magic? It's magic. It's literally magic. I mean, well, when you do that, you win a Nobel Prize, right?
Yeah. So is that like how you've seen the IBM's tiniest movie in the world, right? That's how they did that. I know they used carbon monoxide because it would line the molecule up vertically.
I don't know if they use so electron microscopy is really complicated, and so there's like scanning tunneling electron microscopes. There's scanning electron microscopes. I don't know which one they used. I imagine it's a scanning tunneling though, because those are usually used for like individual atom visualizations, I think. Okay. So,
you know what? I just thought of something where quantum mechanics affects us in the real world, and that's when we're trying to do microscopy or using telescopes, because the light gets, I can't remember what you call that. The light gets separated.
That's actually a fairly classical effect.
Oh, okay. Oh,
you're talking about
we're treating the light as if it's just a wave.
Yeah.
Okay.
It's spectral aberration or something like that.
Yeah, I think that's right. There are techniques for this. If you've never heard of the YouTube channel Journey into the Microcosmos,
I love it. It's so good.
Did you see when they got their new microscope that has the it just showed
blown away. It looks like 3D.
Yeah, it looked like it was made of corduroy. The organism, and I was like, I can't. And apparently, it just corrects for those that thing. I looked into it because I was so blown away by that I had to know what was going on. And I don't really remember very much of it, but yeah, I don't either, but it's super cool. yeah, it's so awesome. Anyways, so now I want to talk about misconceptions. So I just kind of have like a list of them and some questions.
Sure.
What would you say the biggest misconception is? My guess is that it's the claim that atoms are mostly empty space.
No, the observer effect.
Oh, okay. So you think that's the number one thing that people like get wrong or whatever?
Well, maybe it's not the most common thing that people get wrong, but it's the thing that's the most devastating when people get it wrong, because it can really change the way people think and the way people act.
Huh.
Nobody's gonna like, I don't know, run into traffic if they think that atoms are mostly empty space or something, right? But the observer effect really, like, I'm sure people have seen like these manifestation life coaches that are like, quantum mechanics teaches that you affect reality. Like it's dangerous, and people get swindled out of a lot of money.
Okay, so it's consequential in that way. Cool. I was thinking of it from just I'm doing the videos about facts that aren't true.
Yeah.
And this seems like the biggest fact that isn't true that people talk about. And it's because you can't think about it as, how do I want to say this? The volume that an atom occupies, the nucleus, contains way over 99% of the mass, but it occupies something like a trillionth of the volume. But that doesn't mean the rest of it is empty space, which doesn't make sense to a lot of us, but it's just because the rules are different, I guess.
It is definitely a big misconception. I guess I just don't. I think I've made a video on it. People were like, "Well, that's weird," and then I kind of moved on because it doesn't. So you're probably right that it is a biggest misconception. I just think that it doesn't really matter, actually.
Sure, fair enough. Absolutely fair enough. So the next one I have, we actually just talked about this. An observer is required for the wave function to collapse.
Yeah, so. Okay, I'm going to go on a mini rant here. Bear with me.
That's totally fine.
Okay, so the trouble with this claim is that in principle, it's unfalsifiable. Because you could do as many tests where you're blindfolded and you have a camera set up, and then you put the camera in storage for 10 years, and then you look at it 10 years later, and then you see, aha, it's collapsed. But then somebody who believes that the observer effect is real, that observers are required for collapse, would just say, well, it just never collapsed until you looked at it 10 years later. And so this is
Schrodinger's cat.
Well, yeah, sort of, yeah. But the thing is this is entirely solipsistic. This basically just says if you close your eyes, the world stops existing. Which
Okay.
I'm like, look, we don't live our lives that way. If you want to believe that, that's fine, but that's not how we do science. Instead, we can run tests, and in fact, this was done. I've made a video on this. It's like this. It was on a paper that I was pointed to, and basically tests like they did an analysis of is consciousness actually required for collapse of the wave function. They did a double slit setup, which is this famous thing that people use to kind of test this kind of thing. And they basically said, okay, first we're gonna have nobody there, or first we're gonna have somebody just like have a camera set up and then just have somebody looking at it. Okay, it collapsed exactly as expected. Then we're going to have a person there in the same room, or we're going to have a person there looking at it, but distracted by something else going on. Okay, it's so like their consciousness is not perfectly, focused on it. Okay, it's still collapsed. Then we're going to have somebody in the same room, but looking elsewhere, doing something else. And then after the experiment is concluded, like 10 minutes later, or whatever, go back and check. Oh, it's collapsed. Then we're going to have them not even be in the room, have the experiment happen, go back and look at it, 10 minutes later, whatever. Oh, it's collapsed. So it's always collapsed. It has absolutely nothing to do with whether there's a consciousness involved, whether there's a person involved. It's just whether or not you're interacting with it. And the camera's doing that for you. You don't need a person there at all.
Yeah. Yeah. So the next thing I wrote down, I think everything you said probably gets to it, because the next thing I wrote was consciousness affects reality. But like all you need to collapse the wave function is a photon. So like if
an electron.
Yeah.
Or an atom.
If no living beings existed, wave functions would still collapse.
There would still be stars.
Yeah.
Right.
We wouldn't know it because we wouldn't be around.
Yeah.
But that's just kind of a philosophical thing. And then, the thing you brought up about solipsism, I run into the same. People try to make arguments, like they make solipsist arguments as if that somehow makes a point. But it's true that there's no solution for solipsism, but solipsism also makes no point. You can't do anything with the argument. It allows you to do nothing. So they think it proves a point that they're trying to make, but it doesn't, nor even could it, like in principle, I guess.
Yeah.
One other thing is like, I don't think I wrote this down, but we think that quantum mechanics is just light or just electrons, and like same with quantum tunneling, but no, entire atoms, and I've heard that entire molecules can behave this way. Like a molecule can quantumly tunnel.
So the biggest example that I've seen, I looked this up a while ago. So the one that I heard about must have been in college, like starting to feel old, 10 years ago, was fullerenes. Do you know what a fullerene is?
The name doesn't ring a bell, but I might
It's
know
a
what it is.
C60 molecule. It's like a soccer ball.
Oh, it's like Buckminster fullerene.
Yeah.
Yep. I know what these are.
You can do the double slit experiment with those.
Oh wow.
And I vaguely remember reading that somebody did it with a protein, like 2,000 atoms or something like that.
Wow.
They may have not done the full double slit, but they showed some sort of quantum mechanical interference. And you have to do these under very, very special, like super controlled circumstances. They have to be like close to absolute zero and all of this stuff. But yeah, this is a thing that you can do. And it just shows we get better and better technology. We're going to eventually have macroscopic things that are quantum mechanical.
Wow. Wow. Yeah. So I think maybe you're the one that told me this, but like I am quantum mechanical. It's just that, like, how do I say this? Because I'm so large, the odds of all of my molecules doing something that an individual atom is observed to do are just so incredibly low. It's like I could quantumly tunnel through the wall. It's just that the odds of it are just so low because of like how large I am, I guess.
Yeah, it's a law of large numbers thing, right?
Yeah.
If the probability of a single atom tunneling through is 0.1%, let's say, tunneling through the wall. Well, you're made of I don't know, let's say a trillion atoms, to be honest. That's 10 to the 24. Avogadro's number is 10 to the 23. 10 to the 24 is close enough, right? So take 0.001 and raise it to the trillionth power. That'll give you the probability of this happening.
This sounds like Sean Carroll wrote that paper where he calculated what are the odds that a grand piano will just manifest itself in space.
Yeah.
And it's
It's
it's calculable, but
Yep, it's just very, very small.
okay, cool. That was the next question. I didn't realize that misconception that quantum mechanics only affects light or subatomic particles. So we're done with that. Next, we touched on this a little bit, but the next misconception is entanglement breaks the speed of light.
It's contentious. It's not even well established. So in the Copenhagen interpretation, it most certainly does. The wave function collapse, it just does. Now, you can't communicate with it. There's something called the no communication theorem. It's a mathematical theorem, very, very strong bounds. You just can't send information with it. But still, something is happening faster than the speed of light. The many worlds interpretation doesn't require it. Basically because collapse never happens in the many worlds interpretation. The idea being that you have two things entangled. The collapse of one causes the other one to collapse instantaneously, regardless of spatial separation. But if there's no collapse required, then there's no violation of there's no speed of light violation.
So another misconception is with like a double slit experiment, is it actually accurate to say that the electron does go through both slits, or do we not really know if that really is what's happening?
Under the many worlds and Copenhagen interpretations, it does go through both slits. Under the pilot wave theory, it doesn't.
Oh, cool.
Because the electron's just a particle. It just goes through one or the other. But which one it goes through, we just don't know. And it's guided by the wave, which does, do all the interference stuff.
Have you seen the Veritasium video where he has the silica oil and he makes little beads? It's being vibrated by a speaker underneath. And if you make a bead with the oil, that little bead will stay on top and it actually moves around. You can do a double slit experiment with it. Yeah. And it will actually vaguely trace out an interference pattern.
Wasn't that a video about the pilot wave theory?
It must have been, yeah.
I think it was.
Yeah, it must have been, because what you're describing sounds so much like that, and that's why it reminded me of that. That's cool. All right, another misconception is people will say, nobody knows how quantum mechanics works.
I want to attribute it to Feynman. It probably wasn't said by Feynman.
I was just going to say that, because I've heard him say something to the effect of, nobody understands, or if you think you understand quantum mechanics, you don't. And then there's another quote that's something like, nobody understands it except the math.
So I think probably in Feynman's time, Feynman did his grad school in like the 20s or 30s. So he was like with the early quantum mechanics people, and they didn't understand what they were talking about. Can I swear? Is that allowed? Should I not?
Yeah, I don't give a shit.
Okay. Nobody had any idea what they were talking about, or had any idea what was happening. But it's not the 50s anymore, right? Yeah. And it is very counterintuitive, but it's one of those things where, so if you were raised in the 20s or 10s, 20s, whatever, of the 1900s, God, I hate saying that. Then and you're only you like in the entire time you're in grad school and college, whatever, you're learning about classical physics, and then there's this new thing that you have no understanding of, but it matches the data. Well, I guess you can figure out the math, but you'll have no intuition for it. They start teaching quantum mechanics freshman year of college now.
Wow.
If you're, I mean, I get maybe sophomore year depending on how advanced you are or whatever. But like, I had 3 years of quantum mechanics. You have quantum mechanics every semester, basically. Another 2 years of grad level quantum mechanics. Like, it just seems like how the universe is. It's just a matter of where you quote unquote raised on it. And I think modern physicists actually do just understand it. Like we just have an intuition for it. That people in the 50s may not have. Now, it is still very strange. It doesn't comport with our intuition, but you work with the stuff enough and you get used to it, right?
Yeah, when I try to talk about what science actually does with my students, I make an analogy I call it the circle of ignorance. So let's say we have a question. So we draw a circle around that question because we have no idea what the answer is. So it could literally be anything. What science does, this is more like of a view of science through the lens of Karl Popper, where it actually disproves certain things. So we make some like test or we do some observations that erase part of the circle. Now, if we only erase half the circle, there's still this very large lens of, we don't know what the answer specifically is, but we know it doesn't lie somewhere over here. And so I feel like maybe, in the 40s and the 50s with quantum mechanics, the angle of the circle of ignorance was large. And today it's just been erased more. It's more narrow. There's still so much that is mysterious, but maybe that's the what it really is. They didn't know what they didn't know, or not. That's not really the right way to say it. They just didn't know. Well, yeah, it's kind of, they didn't know what they didn't know yet, I guess, sort of in a way. Whereas we've disproved questions that they didn't have answers to yet, I suppose.
I think that's partially it, but also just like, because it's now an integral part of physics, the pedagogy has just gotten a lot better. So people can develop intuition much more effectively.
Yeah.
Pedagogy?
I say pedagogy. It's a teacher word.
Fair.
So another misconception, the quantum realm means that the universe is indeterminate.
If you take the Copenhagen interpretation, it does.
Okay. So what I was thinking that what I was thinking is what it really means is well, I guess this is actually really just Heisenberg. So you can't know two different things at the same time, but that's not the same thing as it literally is indeterminate, I guess.
No, so the Copenhagen interpretation really is genuinely random.
Okay.
You make a measurement, and there is no, like, if the Copenhagen interpretation is correct, there is no possible way to determine. There's no amount of information you can gather to determine which outcome it'll be. All you have is a probability. The many worlds interpretation, again, my preferred one. It intertwines really nicely with my philosophical perspective, so I liked it quite a lot. It is completely deterministic. There's no probability anywhere. Even the Heisenberg uncertainty principle, it's still there, but it's completely deterministic in that, like, the question of like, well, which one did you measure? Well, that was already determined. So it's like all there is a wave function marching, like, completely deterministically marching forward. The only thing that's not deterministic is just which branch you end up on. But you end up on every branch, so it is deterministic in that sense.
Yeah.
But which one's the real you, right?
Very true.
But yeah, so it depends.
Okay, cool. So it's not a misconception depending on the framework, but it is depending on another one. Cool.
The thing that I would say about that is that people take it like the popular conception of quantum mechanics. Maybe the tide is changing a little bit because of Sean Carroll and things like that. But the popular conception of quantum mechanics is just the Copenhagen interpretation. So there's just this belief in people who read pop sci articles that just the universe just is indeterminate, and that's not up for debate. That's just how it is. The wave function just does collapse, and that's just true. But it's not. Like, this is contentious. It's not ironclad.
Okay. That's all I could think of for misconceptions, but is there something else that you like commonly hear? I assume you just hear a lot of the woo stuff, and that's the biggest
so
thing.
Much of the woo stuff.
But that's just kind of the consciousness thing that we already went over.
Yeah. No, I think you hit the nail on the head for most of those.
Okay. So I have a couple other we're good on time, right?
Yeah.
Okay. Good. I got a couple other things. One is just random things, and then you made the video about string theory is a theory, and then I don't know if you saw the video I made in response to that. For some reason,
I did. I watched it. Yeah, no, it didn't. My videos haven't been getting sent out a whole lot either. I'm kind of mad about it.
I don't know what the deal. Well, it was just that one for me. For some reason, TikTok was like, nobody wants to know this. I'm like, well, I thought it was a cool. So, I wanted to end on that, but
that's fine.
So just kind of like some random things, and this, a lot of this I learned this morning. So. I assume you know who, oh shoot, what's her name?
Sabine Hosenfelder.
Yes. How did you know that?
Because there's not very many women in physics.
Well, unfortunately, yeah. Man, I watched a couple of her videos this morning, and this is where came up with some additional things to say. And one of the things was she actually said in 2006, there was a paper published that says if humans have free will, then so do particles. Like it's been mathematically proven, basically. And it was by John Conway and Simon Cochin. Do you know anything about that? Like, do you have any thoughts about that?
No, but it sounds reasonable because, I mean, I don't think that humans have free will, so I'm not worried about it. But it sounds reasonable. I mean, where would the free will come from if not from particles? I mean, my guess is that they're just taking this position that, like, well, if free will exists, it's not spiritual, it's still some physical property, and so it would have to emerge from particles. That'd be my guess.
I think the idea seems to stem from, like, the photon either can go through slit A or slit B, and because there's a probability that it'll go through one or the other, that would be exactly like what people that defend free will say it is. The probabilities, but it's,
they think that it's a result of like quantum effects or something like that. Yeah, I see.
Yeah, something like that. So okay, I just thought, I was like, there's actually a paper that proves that, but it doesn't prove that there's free will and that particles do. Just if we do, so do particles. But it would also mean that if particles don't, we don't. And I think most people's intuitive notion of, like, you know, particles is that they simply don't. And that's the most common thing that's how I debate free will, because I tell people, like,
you should link me that article, by the way.
I will.
Okay.
I don't know what consciousness is, but it seems to be an emergent thing that comes from brain states, and brain states emerge from neural pathways, and neural pathways emerge from the activities of neurons, which the activities of neurons are mediated through neurotransmitters. And so it's all deterministic things all the way up that produce it. And I don't see how there's any room. If free will were real, then there would have to be some top-down governing force that isn't who we are, that would be non-physical. And just so little of that makes any sense. But
it's called a soul.
Yeah, well, it could be anything, but yeah, it could be a soul. But that's kind of outside the scope for this one. Maybe you'll have to come back and we could talk about that.
Sure.
Are quantum jumps indeterminate? And also, what are they? Because she was saying that she was implying that people think they are. I think she said she just doesn't believe in quantum jumps.
So I should preface this by saying that I'm sure Sabine Hossenfelder is a brilliant physicist. I don't love her. This is a podcast. I probably shouldn't disparage people. So, but I don't love her. I'll just leave it at that. But she's probably right about this. Namely, like, I actually have a video on quantum jumps, and I talk about Scott Bakula. As a throwaway joke. But so the idea is that a quantum jump was the original idea of a quantum jump is that you have electrons at various orbital energies, right? They're at different, like, in different shells. And the idea is that there's, like, kind of this spontaneous snapping of it's in one orbital shell and then it jumps down to the next and there's no in between. But that's really not what happens. It's true that it starts off in one state, it ends in the other state, but then what happens is that for some reason there's some perturbation that happens. Like, it's caused by it'll be caused by some stray photon or something like that, perturbing the system. What happens is that perturbation, because it's in a higher energy state than it should be, than it could be, that perturbation leads to an instability. And so what ends up happening is you have a superposition occur. You have it starts off in its higher energy state, and then quickly over time it superposes with the lower energy state. So you basically end up with a gradual mixing. It's never between the two, because if you measured it, it would always be in one or the other. But the probability quickly goes from 100% in the high energy state to 50% in the high energy state, 50% in the low energy state, to 100% in the low energy state, 0% in the high energy state. It's just a quick, smooth transition.
Oh, okay. So when I teach this is how this is why metals glow, and this is why the hotter they get, they change. This is how I teach it, at least. Metals start to glow red first because that's lower energy, and then orange and yellow because the electrons, they're absorbing that energy, so they move up and I
Yep.
tell them it's just like pulling on a guitar string. It doesn't do anything, but when you let go of it, the energy has to be conserved. So the energy it absorbed has to do something or go somewhere. Now in a string, it emits sound, but with
Yep.
these metals, if it's the right kind of energy, it'll release light. And so I guess I say it just goes from energy level, for example, like, I don't know, 4 to 2. I guess I never really say it's instantaneous. Maybe I do, but
The other thing that's that's a confusion for a lot of people is they think of these orbits as just being like kind of like planetary orbits. So like it would be jumping from like Mars to Earth and it doesn't pass in between. But it's all that's happening is that there's like a gradual like shifting between the two states.
okay.
And that's one of the weird things about quantum mechanics. You can have superposition. You can be in two states at once.
That's weird. That's interesting. What the heck is the next thing? Oh, right. Did we answer whether or not they're indeterminate?
Oh, yeah, no, they're determined. They're determined. They just happen basically instantly and seemingly for no reason. So,
okay.
I actually did research on this for the video I made a while back, which did poorly. It's such a shame because the videos you put the most research into do the most poorly for some reason. There's the idea is that if you could perfectly isolate an atom, perfectly isolate it, and then put an electron in a high energy state, it would never decay, ever. Because it's the language is it's a time independent Hamiltonian, and it's in an eigenstate, which means that it's stable. But the thing is that even if you turned off the lights, there's still cosmic microwave background radiation everywhere, right? True. So there's always going to be stray electromagnetism somewhere, and so so at any moment in time, every atom is being perturbed just so slightly, and that's enough to kick it down.
Wild.
This is all to say, it is determinate.
Yeah.
In the sense that it needs something to kick it off.
Yeah.
But it just always happens.
Yeah, because determinate just means it's whatever it does is dependent upon prior conditions or past events or something like that.
Yeah.
So you're just saying if we somehow removed the influence of all things, it could remain in a higher energy state indefinitely. But it's not like It's not violating the conservation of law or conservation of energy or anything like that. It's okay. Cool. So have you noticed, I think you have, because I saw you laugh in the introduction, but that Marvel is just using quantum as a cheap plot trick over and over and over again.
I saw Quantum Mania. I was flying back to the States a week and a half ago. And when you're on a 9-hour plane ride, what are you going to do but watch bad movies, right? So I watched Quantum Mania. It's actually a cute movie. I just wish it had nothing to do with quantum. No spoilers. They go to the quantum realm, and it's just like a world down there. They could have just gone to another planet. It would have been the same thing.
Yeah, it's Endgame used it. The Ant-Man movies obviously use it. Did you see the new Flash movie?
No.
They kind of use the idea of alternate realities in there. It's not exactly quantum because he does this by running so fast that he just gets access to like it's kind of
Speed
weird.
Force. What can you do?
Yeah, whatever. But I just worry that the movies are going to get to the point where it's like, yeah, let's just use this because we can't think of anything creative. So let's think of something confusing to make people think we're being like philosophically deep.
It's either that or wormholes, right?
Or wormholes. Yeah. So.
Or the multiverse, which they also use in Marvel.
Yeah. No. Yeah. That's kind of in Infinity War. They basically when Hulk talks to, what's her name? Not the Guardian, but what's her name? The bald lady that.
Yeah. It's the whole thing with Doctor Strange, right? Like he accesses the multiverse or whatever.
Yeah.
Multiverse of Madness was one of the movies.
All right. Well,
it's a good movie, but
I find it to be a little bit cheap and it's just kind of cute. And Hollywood doesn't really try. They try as little as they need to most of the time. So it's just an observation, I guess. So this is kind of a funny, a personal one for me. So, We have no idea why water goes turbulent. Do you have any like insight into that? Like, what's the why? It seems like the biggest mysteries in the universe are quantum mechanics and why does water do this, or any
So
fluid, technically, I guess.
you're talking about the Navier-Stokes equation. Um, I don't know if you know that that's the context of what you're asking about. But
No, but I read this in a book. I think it's a quote from Heisenberg. He said, when he dies, if he meets God or the devil, he'll ask him two questions: why relativity, and why does water go turbulent? And he famously said, I think God will know the answer to the first one.
there's this really, really famous equation called the Navier-Stokes equation. Um, and I have to Google because I don't actually know if it's a Millennium Prize, but it's a differential equation. It's just one of those laws of motion. That it's yeah, I don't know. It's a Millennium Prize from the Clay Institute. The idea is that it basically tells you how fluids behave. It tells you how they flow under pressure and temperature gradients and all of that lovely stuff. The trouble is the equation is horribly, horribly, horribly nonlinear. And it's a second order differential equation in three variables, and it's just very, very bad. And so this is just a math problem at this point. You'll win $1 million if you can prove it, but there's questions about whether this math problem has solutions. That's it. That's the whole thing.
We just don't
We just don't know. We just don't know. Now it's a math equation, so we can approximate it, and for all intents and purposes, we do, and it works very, very well. It's a question of existence and uniqueness. It's a thing that pops up in math a lot, where basically, given a set of input data, can you uniquely, or can you prove that input data will lead to a solution that can keep going forever, like it doesn't just terminate and then explode, and will it lead to a unique solution? That's the problem, and we just don't know if that's the case. And the thing is the Navier-Stokes equation, because it describes fluid motion, describes turbulence, and turbulence is chaotic, which is why it's so difficult to describe, or difficult to even talk about the Navier-Stokes equation, because chaotic systems are very, very complicated to describe.
I wonder, it would be cool to talk to a visual effects artist and ask them, when you have to recreate this, is this a huge problem? Do you have to do it in a because I wonder if this would mean it's very hard to make a simulation that does it, or if it's actually kind of easy because you can approximate it or whatever.
I haven't thought about that, but it's probably quite hard. I mean, I'm sure you remember. I don't know. Did you play video games? Do you still play? I mean,
oh yeah.
So water graphics haven't only got good in the last maybe 7 or 8 years, right?
Yeah.
They were just kind of glassy, and now they're really, really good. Just I imagine just in advances in simulation techniques and things like that.
Yeah, smoke is another thing that's just really hard.
Also a fluid.
Yeah, I remember video games are just so fun because I think back of video games that made leaps in things. Like Crysis, famously, their lighting engine, everybody was that's a game that looked ahead of its time. Most games don't, but that one did. I remember Call of Duty 2, their smoke simulations looked so real back then, but really all it was it would be it would start off as a cloud of smoke, and it basically just stretched and got bigger. It didn't really transform, but back then it looked amazing because before then, smoke was just a fog that just gradually got more and more dense, and that's not particularly interesting or special. The last random thing, and this came from I watched Sabine's video on. Well, I did a couple things. So this has to deal with, can an event in the present really affect an event in the past? So I'll frame this by just going over how I got here. I rewatched the PBS Spacetime video about the delayed choice quantum eraser. And I watched that and I was totally mystified by it. I always have to remind myself how the hell it works.
Me too.
Because it's confusing. But then I saw that Sabine made a video about it, and she said, no, the delayed choice quantum eraser is not special. And from what I understood, she said, the reason it's actually not special, that it doesn't affect events that happened in the past, is because the interference pattern that's revealed by looking at the two detectors over here, they are just two non-overlapping halves of a non-interference pattern.
Yes.
So that's absolutely
If you
the
add,
case.
if you added them together, you would just get the non-interference pattern. Yeah.
Okay. Okay. So, yeah, it kind of bums me out because I want to think that events in the present uh, change which slit the electron went through in the past, because that's just so bonkers and cool. But it's also nice to know that we know what we're talking about.
Yeah. In fact, so I have a video on this from a while ago. Must have been one of my earlier videos. And I basically based it off of Sean Carroll's blog. Sean Carroll's like, I emailed that guy a few months back because I read an article of his. I'm just like, hey, this is really cool. Can you answer some questions? He never got back to me, of course. But yeah, he has a blog post on the delayed choice quantum eraser and how you can understand it using the many worlds interpretation, and it's quite a slick description. So to anyone interested.
Yeah, I like listening to him more than any scientist. I feel like I really like Neil. His Star Talk thing is so cool because they go all over the place.
Yeah,
And he definitely knows so much, and he's fun to listen to, and it's really funny too. Is the other thing, but Sean just makes it see. I don't know. He just knows what he's saying. He just seems
he's
like
very precise.
Yes. He never says or which is every other word I say sometimes when I'm talking about stuff like this. And he requires no processing time. He can just talk about so many things. It's so cool.
Yeah.
Okay, so the final thing is what counts as a scientific theory. So I've thought about this, and what I did was I did some digging. This is more philosophical, I guess, but I did some digging into like schools of epistemology, or how you do epistemology. So like somebody like Leibniz or Descartes, they were rationalists. They were pure rationalists, and math is pure reason. I can't think of anything else that math is. It seems like it's just pure reason to me. So they would think that you can know something or you can prove something through reason alone. Descartes never thought that a human could actually do this, but it's in principle doable. But most of us, like people like me, or when we think about science, we think of science as it has to be empirical. And an empiricist, which would be like David Hume or John Locke, or like an experimental scientist, is you have to have something observed, right? It has to be empirical. So we can get into like what makes a theory, why something that seems like it's almost purely mathematical, like maybe string theory, still counts as a theory, even though it doesn't really have an empirical lens to it. We can get into that in a second, I guess. But would you say that quantum mechanics and like theoretical physics, are they more like, would you say that they're more rationalist or more imperialist, or are they just kind of both? And also, would you say it's more metaphysics than science? I've heard that Copenhagen is metaphysical, the Copenhagen interpretation.
So so asking about interpretations at all is, people have thought it's been said that in any interpretation is metaphysics.
Okay.
I kind of disagree with that. I think it's actually possibly testable. That's neither here nor there. I don't remember who said this, but quantum mechanics is by no means a rationalist approach. If only because I think somebody said of quantum mechanics, who ordered that? Like nobody wanted it to be this way. The universe behaved in such a nice and beautiful way prior to the year 1900. It was like clockwork. You could predict things with perfect accuracy. All you had to know was the initial conditions. Everything worked out wonderfully. You had gravity, you had electromagnetism, and then a wrench gets thrown into it because of the data, because of an experiment that was done, and now we're like stuck with this messy Hamiltonians and Hilbert spaces and uncertainty principles and all of this stuff, and nobody ordered that. So no, it's fundamentally an empirical piece of science. Now, to solve some of the problems, especially as you get into things like quantum field theory and things like that, you have theorists coming up with ideas. sometimes driven by data, sometimes as in, look, we have this problem that we don't understand, maybe I'll come up with something brand new. But for the most part, it is entirely empirical, I would say. In fact, arguably, relativity is more of a rationalist view. Einstein sat down and had a thought experiment.
True.
And came up with a series. Now, he was motivated by experiments as well. He was motivated by Maxwell, who was an experimentalist and sort of a theorist. He was motivated by the Michelson-Morley experiment and so on. But in some sense, he kind of just sat down and was like, I'm going to have a think about what it's like to write on a beam of light, right?
That's awesome. So, like, with regard to scientific theories, without trying to repeat too much of what I said about it is I didn't try to answer what is a theory, but I tried to explain why people like me who aren't scientists kind of get confused about it. So, like, we have, like, string theory, which hasn't so far as I'm aware, produced anything empirical. But we still call it a theory because, to me, I think that string theorists are scientists. I still think that they are.
Someone called them mathematicians.
Yeah, well, I guess. So I've also heard, like, and like theoretical physics, it's science, but I've heard you debate, like, you were debating Angel once, and he told you, like, that there was a paper that was published that proved something about the holographic universe or something like that. And you said, well, no, it's just a paper. There's never been any experimental proof of it or whatever.
Yeah.
So that's where I say maybe what's really going on is some of these scientists, they're working in a rationalist, like their epistemic approach is rationalism, whereas others it's empiricism, but it can still count as a theory as long as they're being consistent with their sort of approach to it.
So, I mean, I'm a descriptivist as far as language is concerned, meaning that, like, I don't care what words mean as long as we know what people are talking about. So, like, look, theorists in particular and mathematicians all the time use the word theory. So it's just important that we know what they mean when they say the word theory. And they don't mean something that's been tested. They don't mean, like evolution. They don't mean like germ theory. They don't mean like, the general theory of relativity and all of this. They just mean a framework, like I said in the video. So, but I don't think it's from a different philosophical or epistemological approach. I mean, like, in some sense, I'm like hardly even a theorist. I'm like closer to a mathematician than a theorist, right? I spend my days working I made a joke to I don't know, maybe we've had this conversation, but I made a joke to my boss here in Europe that, we're having trouble with these low-lying dimensional cases like 4 dimensions. So maybe we just work in 39 dimensions and then just, we'll deal with the details later. And like, that's very much a like, how could this thing that you're working on have anything to do with reality, right? But the point is that what a theorist does today, and really since the 70s perhaps, is very, very different to what a theorist has ever done in the past in physics. At least as far as like quantum gravity theory, particle physics theory, these kinds of stuff. And the reason I say that is because we have nothing to guide us. We have no new experimental evidence that is mysterious. All of the current models are so accurate. There's just nothing. But we know that something's going to go wrong. We the quest for quantum gravity is a real thing. It has to exist because we know that black holes exist. We know that something happened in the early universe, but we have nothing to guide us on that. So you end up with people not looking towards experiment, trying to verify and understand poorly understood data, but really trying to come up with an idea in some sense from a purely rationalist perspective and just be like, look, we know something has to work. Let's just try to think about it really hard and figure it out. And it's almost out of necessity that it's become that way, because there's just not the empirical approach has just failed us for the last 50 years.
Yeah, and that sort of is the quote unquote crisis in physics. It's like we haven't made it, like, we discovered all these particles and all this stuff, but we're not really, we still don't have answers to some of those questions that are almost 100 years old and stuff like that. And
yep.
It's kind of like the LHC too. It's like after the Higgs boson, what? Well, so far almost not nothing, because it has some sort of like trickle out effects.
There was like the tetraquark and pentaquark discoveries, which were kind of neat. But again, that's like kind of, yay, we confirmed that something exists that we thought existed. So there's no surprises.
I didn't realize this, but it's going back online for the first time in like what, 4 years or something like that.
I think they had to do, well, yeah, I don't know how long it was offline. I know that they take it down regularly for like maintenance and stuff, and they have to replace all those stuff. So maybe it's been 4 years. I don't know.
God, that's just like how many experiments have they done there? I don't. You'd think it's. I just in my head I'm like, yeah, isn't it on like all the time? Isn't it like a microwave where they're just like doing stuff multiple times? But
so there's multiple experiments running simultaneously, right?
Yeah. So I have one thing that I thought of as you were talking, and then I don't really have anything else. But what's the difference between a theorem and a theorem with a U and an E?
I've never heard a theorem with a U.
I think one's like math, one's math, and one's like science or something like that.
Okay, so I've never heard of a theorem with a U. I go to Wiktionary and it says misspelling of theorem with an E.
Oh, really? For some reason, I was thinking there was something different. So maybe it's just theory and theorem.
Theory and theorem. There is a difference there.
Oh, weird. Okay. We'll probably I'm just going to pretend that I never said that.
Okay.
140. Because it just turns out I just didn't know what I was talking about.
If you want, I can talk about the difference between a theory and a theorem.
I thought
that's useful.
Sure, let's do that. Okay, so I'll
sure. Go ahead.
Do this. So the last thing I can think of is like, what's the difference between a theory and a theorem?
One is the job of a physicist or a scientist. The other is the job of a mathematician.
Okay, that's what I thought.
Yeah. So theorems are true. Theorems are they're just always true. You have a set of assumptions, and then given those assumptions, something is true. If those assumptions are false, then maybe the thing's not true. But if the assumptions are true, the result is true. A theory is, we just talked about that. Theory is describes something about physical reality. That's it.
Sure. I guess sort of, I did think of one other thing. I never really got I've heard you kind of describe it like, what is a theory? I've heard you say they're just models. That's all they are.
Well, which definition?
Well, I don't know.
Yeah. So okay. So we can both agree that the lay definition of a theory is just a guess, and it's a very silly definition. But I would say that I'm repeating what's in my video. I would say that there's two other definitions of theory that is used commonly in academic circles. There is this, or academic adjacent circles. There is the science communicator version of a theory. And I don't even know how old this notion of a theory is, but it's the idea that it is a model that accurately describes the world around us. Plain and simple. It's been experimentally verified. It makes good predictions. It's falsifiable. All these lovely things. And then there's the word theory, as is perhaps, at least in my field, more often used than that definition, which is just a framework. It's a collection of it's like a collection of paradigms, a collection of structures, perhaps, collection of ideas and linked concepts that kind of describe a thing in its entirety. So something that I work on, and this is used in mathematics too, by the way. I work on the theory of conformal invariance. So I'm developing kind of a scaffolding. I don't have to define those terms because it's not relevant. Doesn't matter. But I'm developing a scaffolding to basically describe the structure of all of these things in a kind of complete way. Now, it has nothing to do with, well, it can be applied to physics, but like it's a mathematical thing. It's a framework. And you could say that or actually, let's even talk about something that is a theory in the scientific sense. Quantum field theory. Quantum field theory has no physical content in it whatsoever. It's just, like quantum field theory it's a framework. It basically is a way to describe fields that behave in a quantum way and obey special relativity and so on. But it doesn't tell you that there are electrons. It doesn't tell you that gluons interact with up quarks. You have to put that in by hand. And so when you have this framework, Then you can build a model from it. You can take your underlying theory, your underlying framework, and then attach stuff on top of it: data, experimental inputs, assumptions maybe about how the real world works, and then you can build a model and test it based off of that framework. But quantum field theory on its own, it doesn't necessarily have anything to do with the real world. There's so many quantum field theories that you can write down that are just completely unrelated to the real world, but we still call it a theory because it's useful. It's like a complete framework. So that's what I would say a theory is. I would say that there's the SciComm version and then there's the scientist version.
Well, I think that's basically all I had. So if you had anything in closing, otherwise, thanks a lot for being here.
Yeah, I got nothing. Thanks for having me.
You're welcome. Thanks for listening.